guess we can start. Okay, so first of all, the supplementary lecture for Tuesday is cancelled because now that you're back to regular lectures with some laboratory at the same time. About us, how we will make up for the missing lectures, I hope that some announcement will come out. In the meantime, I don't know. Okay, so basically, what we did in the previous lecture was to develop the mathematical tool to do a summation over occupied states when the occupation is defined by the Fermi probability. It was somewhat complicated mathematics, but at the end we got to some kind of formula, and we would want in this lecture to use this formula in order to calculate the heat capacity of the system. Okay, so let's just sum up the results. So in general, in my garbage bin. If we have an integral of the form we showed that we can write it down as okay, so that's what we did in the previous lecture, somewhat painful, but that's the formulation that we developed, and that's known as the Sommerfeld summation. Now, for our purposes, we'll never move beyond the second term here, but in principle, one could get more terms. Okay, our aim was to calculate the total energy per unit volume and the number of particles per unit volume. Okay, for these cases, for the first case, HE is equal E times GE. In the second case, HE is equal GE, and we'll just plug into the formulations that we developed in the previous lecture. Okay, the reason that we used HE and not each one of them separately is to simplify the derivation. Okay, so at the end of the day, what do we need in order to plug into this expression up to the second term? We only have to know what is H prime in each case. It just performs the derivative.
שאין תואם ל-H, אבל תציג בשורה התחתונה שתואם לזה ספציפית שמופיע כאן.
I'm just looking at the integrals. Here, H is GE. First derivative of GE is first derivative of GE.
Okay, just make sure.
Here I have a multiplication of E and G. So derivative of E, derivative of G. That's all. In each case, I substitute E by mu, as in any Taylor expansion. Okay, so let's see what we get for n. Okay. Of course. Okay, I just substituted. So, what is my purpose in calculating n here?
Find mu.
Defining mu. I'll assume that mu doesn't change much compared to EF, which is the Fermi energy. Temperature is small, and as we argued in the previous lectures, the changes in the occupation won't be big, and therefore the changes in mu can't be big. Okay, so I can go and rewrite what's written here. Okay, you can stare at me and say, we don't understand. What did you gain by separating the integral to an integral till EF and from EF till mu? What I gained from it is that this is a small region. And if I'm considering an integral on a small region, can assume that GE doesn't change much in this region. So I can rewrite what's written here. Yes.
We still didn't say what mu is.
The only thing I assume that mu is not very different than EF. I still don't know what's mu. The whole calculation here, its purpose is to find what is mu.
Oh, now you just have a simple like linear algebraic equation.
Now I have, we'll see, just a moment. The crux of the approximation here is in this term. What is equal this term?
Number of particles in T equals 0.
Which is n. The number of particles didn't change. So this must be equal to minus this. Now I assume, again, mu and EF are not so different, so I can assume, because corrections to mu will depend on t, and here I'm taking the derivation only till t squared, so additional corrections don't matter. And I'll divide by GE. And get mu equal EF so I got an expression for mu. Since I know GEF, and I can know the derivative, so I write myself here.
KF, right? Yeah.
KF, right. And now I can stop a moment and see if I'm self-consistent. KBT should be much smaller than EF. That was the assumption of the whole procedures that we did here. Indeed, this correction is small. So I started from assumption, and it's very important when I end the calculation to recheck that my assumption actually holds at the end of the calculation, and indeed it does.
What is the N and the G?
N, it's the same N that we had.
And what is it in the
And here I used this dependence on E, performs the derivative, divided. Okay, next integral. So we performed the integral on N, we got mu, we can move on to the energy. So I want to keep this on the board, so I'll erase this part. Okay, I'll again use the fact that when I'm doing an integral between 0 and mu, I can divide it till an integral till EF and EF till mu. And plus the second term. And here the expression is more complicated. Okay, I just use the expressions that I developed and substituted the terms. Okay, simplification. This guy we solved in the previous lecture. Okay? If you don't remember, refresh what we did in the previous lecture. Same trick. Same tricks that we used in the previous case. And here, since the corrections to mu are of order t square, and I have already here a t square, I can replace mu by e. Okay? How do I progress from here?
We can substitute the value of mu.
So this guy is exactly equal to this guy. How does it do? Which is equivalent to substituting the value of mu. It's even more transparent, and we're ending up with first term doesn't depend on temperature. Okay, I'll just perform the derivative of the second term. And and using the definition of GE appearing here, I'm ending up with and this is a very interesting result. If I would naively calculate the classical heat capacitance for electrons, what would I have gotten? 3 times nkb times t, and the t goes off in the derivative, 3 nkb. Well, I have n, I have kb, I have some numerical factor, but the important thing is not all of the electrons are in the game. Only a ratio of kbt over EF. Only those guys that are close to the Fermi surface are in the game. All others are irrelevant to heat capacity. So quantum mechanics compared to classical physics tells you that only a small fraction of the electrons contribute to the heat capacity. Therefore, the heat capacity from the electronic constituents of the matter is much, much smaller than what you would have expected on classical grounds. And we understand why. The reason is simply because of Pauli exclusion principle, which tells you that most electrons are inert, are not able to receive additional energy. I change the temperature by a bit, and only those in the external part of the Fermi surface can play a role. All others are not in the game. Okay. Now we completely switch gears. The last few lectures we have been dealing with the case where we're interested in thermodynamical properties of the systems and the influence of quantum mechanics on these behaviors. And we assumed that that basically we can consider the electrons as particles in a box. We threw out the lattice and got to the point of understanding the behavior of heat capacitance. Now I want to return the lattice into the game, and we will see that the fact that we have a lattice in these systems completely changes the quantum mechanical properties of the system. It's not similar to free electrons. Nevertheless, at some limit, it's a nearly free electron system. And the main goal in the rest of this lecture is to understand what happens when we put in a lattice into the game. So what would be the main influence of the lattice? question to you.
Maybe reflection. So far we're talking about reflection of waves.
Right, the waves will, it's an electron in a potential. You know that electrons in a potential behave differently than free electrons, but in some sense, thinking along these lines will actually push you into questions regarding how does the potential exactly looks like, and that makes life complicated and you're drowning into details. And at this stage, I don't want to go into details. I'm looking for a much more important difference. And probably you're not yet so accustomed to think about physics in this way, but one of the most important properties in physics is symmetry. Basically, if you understand the symmetry of the system, you can make predictions on the behavior of the systems without going into details. That's very important. Actually, you have encountered it. Okay, you can accept conservation of momentum as something that comes out of Newton laws, but you can also think about it as a symmetry in space. You have seen it in analytical mechanics. So the fact that you have conservation of momentum, you could have garnered out of symmetry. Same conservation of energy. The fact that I have a symmetry in time, it doesn't matter if I do something now or sometime in the future or sometimes in the past, forces you to the conservation of energy. Once I have a lattice, I have also some kind of symmetry, which is the lattice symmetry. I move from point R to point R prime in the lattice, I see the same environment. And that makes a lot of difference on the solutions of the wave function of Schrödinger equation. Okay, before going into the mathematical details, what do you expect the wave function at 2 points that are separated just by lattice vector? Or moment, so let's assume I have some kind of lattice. with some kind of lattice vector. And I look on the solution for Schrödinger equation here at some point, has some solution. And I move by R to another point R plus R. What do I expect the wave function to look like?
Same, no, it's not, because we have symmetry, so if we wanted to...
So we could have thought that the wave function is the same. But what at least should have been drilled into you in quantum mechanics, is the wave function a physical entity?
No.
No. It's not.
Only its absolute magnitude squared is a physical entity.
Exactly. Or any other operators that I can use on it and calculate some observation of another physical quantity. But the wave function itself is not a physical entity. Therefore, psi r is not necessarily equal to psi r plus r, but psi r squared must be equal.
Yeah, the momentum would necessarily be different.
Excuse me?
The momentum would necessarily be different.
Hmm?
The momentum.
We'll see that we will have a concept of quasi. But at the moment, let's keep it simple. If I'm looking on the wave function at a point, its absolute value squared should be the same, because that's a physical quantity. And since there's no difference between this point and this point, there can't be any difference in the probability of finding an electron at these 2 points. And this is a probability. Okay, so this is a mental picture that we are keeping in order to understand what we are doing here in our mathematical formulation. We want to take this rule and learn what it actually implies on the wave functions. You can almost immediately guess what it means.
Phased only.
Exactly. The 2 wave functions should be equal up to a phase, because the phase squared is equal to 1, and it doesn't go into the game. Okay, so what we are doing here in the rest of the lecture are electrons in a periodic potential. The main feature of the lattice that we're taking into account is that the potential must be periodic. And we can write down the Hamiltonian. any lattice potential will come into the game here. And the fact that it's a lattice means that the potential when I'm looking at a different point which is at distance r, big, large r, from the point that I'm interested in, it must be the same. That's periodic. Okay, and we will prove a theorem that is known as Bloch theorem. Which states okay, so basically this is in line with our intuition. There is a phase part and a periodic part. U is the periodic part. E to the power I k dot r is the phase part. And the phase seems to have some connection with free electrons. And we have here k, but we have here an additional index n. We'll understand further on what does it mean. And if you want to see free electrons basically you can think of it as a case where the lattice distance goes to 0, and therefore U must be equal at any point, meaning a constant, meaning you're going back to the solution of free electrons. Okay, we'll prove Bloch theorem using two different methods, which each one of them sheds light on different aspects of the Bloch theorem, or the behavior of electrons in a lattice.
What do n and k represent?
Two quantum numbers, n and k. Why is it two numbers and not just k?
Because it's dimensional.
Because you have your k's will be restricted somehow, and you need another quantum number. We'll see. So basically what Bloch theorem tells me is that if I'm looking right? first way of proving it, we will define an operator So we defined an operator, we haven't yet, we will define an operator TR, which we name the translation operator. Operators, as usual, do something to the wave function. Okay, so the translation operator, when we apply it to a wave function, to any function really, we move it from point R to point R plus R. Want to ask something?
Huh? No.
Okay. Now I'll argue that this operator commutes with the Hamiltonian. How do I prove it? Perform a translation on h times psi. Why? That's part of the commutation. Why? Simply that's what the operator does. It moves you from R to R plus R. But the Hamiltonian is periodic. This part doesn't depend on large R at all, and this, by definition, doesn't change. So it's equal to H. Okay? But this is equal to and therefore So the translation operator and H, the Hamiltonian of a periodic lattice, commute. What does it mean that two operators commute? Now,
They share some states together, like some immediate states.
you can write a basis
Once you know both.
which is a basis for both operators, which is composed from the same eigenvectors or eigenfunctions. Okay. That's the meaning of commutation relation between two operators. Okay, before I'm continuing with that, well, actually, I want to draw your attention to another property of the translation operator, and that's what happens when I consecutively perform two translations. First translated to R prime and then to R. It's as if I performed one translation to R plus R prime. Actually, the order is not important. Where in physics the order is important? Rotations. If I rotate 90 degrees around one axis and then something else along another axis, it's not equal to the two rotations in the changed order. That's why, by the way, all the laws of angular momentum in quantum mechanics are much more complicated than the laws for simple translation momentum. Okay. Should have it here. The index R, because could be different for a different translation. Okay, what happens if I take an eigenfunction and perform two translations? I'm allowed to do it? Of course I'm allowed to do it. This is a number. Can move it before the operator. Okay. But instead of writing it in this way, could do it in one translation. Let's look for a specific case. CR. Instead of, let's write down explicitly CR. We're going back to the beginning of the semester and reminding ourselves that R could be written as a combination of three basis vectors, A1, A2, A3, with some numbers before them. Right? I'm moving it first in A1, then in A2, then in A3. Instead moving it in one direction, doing the whole jump, I'll do A1 after A1 after A1.
Why is there an arrow over N3?
What function follows all these rules?
Exponent.
Exponent. which is exactly Bloch's rule, Bloch's theorem. Because this tells us exactly that appears. Second way to prove Bloch's theorem. I will take my Hamiltonian and wave function and perform a Fourier transform. Okay, can always do that, right?
Because the function
Excuse me?
is non-employed.
Just any function I can write down a Fourier transform. That's if we are approaching it from a mathematical point of view. From a physics point of view, why can we do it?
The problem has periodicity. It's periodic.
Even if it's not periodic.
Yeah,
E to the power IQR is a basis of my Hilbert space. And I can write any function with the basis, right?
Yeah, but in a closed area.
Yeah, I'm thinking here about a finite lattice with periodic
But
boundary.
didn't we say that the lattices should be infinite?
If you remember, any solutions that we did there had periodic boundary condition, exactly to avoid these problems.
We call it periodic, so we can say there are finite areas that are repeat themselves.
Okay. I can also expand the potential as a Fourier transform. Here I'll write down explicit what are the terms. Here the function is periodic. I still don't know about this. I'm going to prove it. can't use it here. But for this, the potential is definitely periodic. Okay, for simplicity, I'll write that the zero term is equal to 0. Does it have to be?
No, it depends on what your initial equation is.
No, it doesn't have to be. The potential could have some average value that is not 0. Does it change anything for the calculation? No, because I can always add this constant in the end. Therefore, I now simplify my calculation by deciding that the 0 term is equal to 0. And if it's not 0, I'll add it in the end. Doesn't matter. Don't change anything. UK is, of course, a complex number. It's a complex amplitude, but I do know that it's equal to U of minus K. Just look on the definition, it becomes apparent. If I'm taking the complex of UK, the only thing that changes here is the minus I here to plus I, meaning that K becomes minus K. Okay. So I have my Hamiltonian. Or let me write down immediately the Schrödinger equation. Okay, and now I want to write it down in Fourier space. Am I allowed? Yes, I'm always allowed to change the representation. Okay, let's look on the first term. CQ doesn't depend on R. This guy does depend on R. Okay. What are the cases that appear here?
Can you form the way that come back, come or return, that we send or maybe sent back to us from the inflection?
It's not physical, it's mathematical. There's a restriction on K. What's the restriction on K here?
The periodic, because the potential is periodic.
Because of the potential is periodic,
So
Pi n over L or something.
K equals 2 pi over R, which is 2 pi, and the R and the
Pi n over L or something.
don't reinvent the wheel. We actually defined what are these K's.
2 pi n or something.
The reciprocal lattice vectors. So this K right? There can't be anything else. Because if there's something else, I get summation that is not periodic. If you don't remember, go back, it's one of the first lectures that we gave here. So, I'm looking on the second term here. So U is this summation over K's, and remember, it's not any K, it's only the reciprocal vector. Just wrote down psi and u as Fourier transforms. In the meantime, I have no restrictions on Q. what did I do here?
Remove the
Find Q values equal to Q.
Yeah, I just defined Q prime as equal to K plus Q. And since the summation over Q is to infinity, the same summation as on Q prime. Exactly, for the discrete summation, it's exactly a change of variables in the integration. So now I go and rewrite the whole Schrödinger equation. Okay, I just copied the two terms that I have written separately previously. This has to be correct for each mode Q. So instead of a differential Schrödinger equation, we get a linear algebra Schrödinger equation. Let me replace Q by K minus G. Then I can rewrite what appears here. Okay. Just replace Q everywhere by Q by K minus G. Am I allowed? Why not? Okay, what did I gain by it? Let me rewrite what appears here. Okay? Too many Ks. And finally, which is Bloch's theorem. Now, after this exercise, you can see why I'm much more enthusiastic about the first way to prove it. It's just much more transparent. Although mathematically this is also a definition, we see the power of symmetry. Okay, so what we'll see in the next lecture is using this Bloch theorem in order to understand the properties of wave functions in a lattice. At the moment, we only wrote the structure of the wave function. Phase times part that is that has translational symmetry. We'll see in the next lecture what actually physics comes out from this this computation. Okay.